So we'll talk about circuits. We did Ohm's law and power law. We feel comfortable with that. If you don't, please see me after class. I can explain that to you. Just basically, we're trying to identify the three components of any circuit. We say we need a load. Otherwise, why do we need a circuit? And we need the complete circuit. Otherwise, there is no circuit. And we need the source, which is the voltage. So we got that in. So what we need now is, we'll talk about the concept of basic electrical circuit. Why do we need to complete the circuit? And what is the point of having the circuit? And what did my freaking thing go? Fine, whatever. So, the basic of circuit. And we'll talk about two types of circuits. Series circuit and a parallel circuit. And how do we distinguish between those? So it's not going to be always just series and just parallel. It's going to be a combination. It's really something very necessary to recognize. Some things has to be connected in series, and some things has to be connected in parallel. I will describe why, and what are the purposes, how do we use them, and what is the difference. We'll talk about series circuit, how they are used. Let's think about that. So, again, we will learn how to calculate the three things that we did before. Current, resistance, and what is this called? Voltage for series circuit. I will do the same thing for parallel circuit. So it's gonna go hand in hand to know the power law and Ohm's law. And I will give you a chance to see that in real life when we do the lab. You're going to connect components in series and see the effects, and you will connect components in parallel and see the effect. Don't worry about that. So, in every system, there's a combination. You're always going to have series circuit and parallel circuit. Let me give you an example of a series circuit. Let's look at this for example. So if you look at these three light bulbs, and this is going to be our hot and neutral. These three light bulbs are connected in series. You agree? They are in series, one after another, right?
Yes.
And the same, this is the hot, this is the current going through it, let's call it A. So the same current will go through the first one, then the second one, then the third one. These are our loads, this is our circuit, and this is our source of voltage. So there are two reasons why we can use, why would we put stuff in series. First reason is control. So if we want to put switches, we're going to put switches in series for control, to on and off the circuit, turn on and off. Second reason is safety. If one of them blow up, the whole circuit will go. So if this light here is disconnected, will the circuit work? No. You know those Christmas lights that you have, if one of them break, the whole thing break, right? Because they are connected in series. So that's series circuit. We need it. It's not a bad thing. It's a good thing. We need it for safety. If you want to put a fuse, thermal switch, high pressure switch, low pressure switch, they are going to be in series. Because if any of those comes up or pops up, the whole circuit goes down. So parallel series circuit is used for safety. And control. So fuse is going to be in series, otherwise there's no need for a fuse. So that's a series circuit. Let's write it down. There's only one path for the current. One path for the circuit for the current to go through. In parallel, we have more than one path. And there's a combination between two of them. I will do the parallel over there, so actually I should erase this. Keep it here. I'm going to do it again, the same 3 light bulbs. So, from this picture, if you look at the 3 light bulbs, and this is the current coming out of the hot line. Stay the same. What happens here at this point? It will divert, it will fork, divide, shift, no, shift is not gonna work. What else? Split. So you'll have 1, 2, and 3. Let's call this A1. It's going to be A2, A3, A4. So they will fork, right? Just like water. If you have different path, it's going to take all path depending on the resistance. So it's going to continue here. And what will happen at this point? They will come back together. So the amperage draw depends on the resistance. You agree? If you have a big pipe of water, when you have small pipe, medium pipe, a big pipe, the pressure at this point is the same, but the water will go through the least resistance. The big pipe will take more water. Medium pipe will take some, and so on. So it will, the amount of amperage will be different depending on the resistance of the light bulb. So let's think about it this way. And those 3 are in parallel. So this is a parallel circuit. And if you notice, if I take this light out, will I still have a circuit? You all agree? Yeah. It's just going to be out, but those are going to work, right? Those 2 are going to work. What will happen to the amperage? It will be different. It's not going to be the same. So, the first key of knowing those problems to recognize are those resistances in parallel or in series. And the key is to look at the current. If the current coming out of each component goes to the next as is, like over there, that's a series circuit. If it's actually it's divided, that is parallel. Because it's not going to always look like that. It's going to look differently in real life. But follow the current, and you will know if those are in series or if they are in parallel. That's the first thing you should do. Recognize this circuit, is it in series or is it in parallel? That's in series. And also ask yourself, if I cut this, will it work? If not, then they are in series. So they can come in different shapes. I can draw it like this. And into a resistance. And this is going to be still also in parallel. We're not going to make a big fuss about it, but at least you can recognize 3 resistances in parallel and series. And it's very, very essential to know the path. So remember the path, one path, more than one path, and a combination. I will put a combination over here. So, are those two in series or parallel?
Parallel.
Those two.
Oh, parallel. I thought you were talking about the two squares.
What about these?
Parallel.
Same. What about this circuit and this circuit? In series. What about this circuit, and this circuit? In series. If I cut this entire circuit, it's in series with the other ones. That's called a combination, and most circuits are combination. So these are in parallel with each other. These are in parallel with each other, but this circuit and this circuit are in series with each other. Easy? Don't complicate things, look at the divide. I will spend some time doing some examples, and the first thing to do is just recognize whether it's in series and parallel, then we can take it from there. So, the path, closed circuit again, circuit is complete. That's a closed circuit. Open circuit, it's not complete, switch is on. So the switch is open and closed. So for a circuit to work, there must be a complete path of electrons to flow through. So if anything is broken, let's say you have a cut in here, none of this is gonna work, right? We had this today in the lab. Somebody was trying to wire an aquastat. They wired everything. One of the wire nuts for the neutral were loose. Nothing worked. You're gonna go check for power here. You'll find power. But you gotta keep tracing the power until you find where is it broken. So you gotta achieve the complete circuit. You need a complete circuit. And I'm gonna keep saying that because this is one of the biggest issues. You go and something is loose and the whole thing is getting power. It gets frustrating. Big circuit. And probably there's a loose nut somewhere, and it's very frustrating to find out where is the incomplete circuit. And that's, well, when you need your best friend, the multimeter, to go and check point by point, like stuff in the beginning, and check the continuity for every component while it's off. Make sure you have continuous circuit. It gets difficult when you have controls, so you have to also check the power at each terminal. Some devices or loads require electric energy, you know that. This is a symbol of simple circuit. Any circuit requires a load, otherwise there is no need for that circuit. So we always need, I'm gonna put that somewhere. It's for here. What do we need for a circuit? You need a circuit first, which is a complete path. Two, you need source. Check your source. And three, you need load. Otherwise, there is no point if the circuit is not doing anymore. Good? Alright. So, series circuit, we talked about it, it's the simplest, easiest to follow because it's one after the other. Switches and control. So if you look at the boards over there, probably you see switches. Remember when you wired the one light bulb? We all did that, right? One light bulb, and you see the switches. Switching were in series, right? And they were all on the hot line, not on the neutral. There's no point in putting a switch in the neutral because you want to cut the power coming into the equipment. So it's done for safety and also for control, whether you want it on or off, but cutting off the circuit, cutting power from that component. That's an example of a control circuit. Are those three in series or parallel? Series. Is this switches and the load in series or parallel? Think. In series, follow the path. Just because they are parallel to each other does not mean they are in parallel. So they are in series. If this goes out, boom. No power. This low or high, there's no power. So follow the path. This is in series, and these switches are controlling whether the motor goes on or off.
Are those the general signs for the pressure switches?
Yeah, not general, but for this
Well,
book.
I don't, you know what I mean.
Yeah. But for this book, this is what they use. You can see something else. This book uses some kind of notation, but every industry uses different signs. Okay. Now we come to some of the calculation. How do we calculate series and parallel circuit? Let's look at that a little bit. So we agreed there's only one path here, right? What would happen to the current going from here to here, from here to here, from here to here?
It's gonna continue to flow.
Yeah, it's gonna stay in continuous flow.
Are we the same?
Yeah. If I put a clip on this amperage, it's going to be the same. If I clip it on here, it's going to be the same. If I clip it on here, it's going to be the same. So let's see what happens to the amperage. It will stay the same. And why is that? Because all these loads are right after each other. The circuit will think of these loads as one load. Because I'm going to go through with this one and this one and this one. So it's going to be like I'm going through one load together. So it's going to be the same current in here, and the same current in here, and the same current in all of them. So the current remains the same. Okay. What about the voltage? Okay. If voltage is pressure, and this is a water faucet.
Depending where you clamp it, that's gonna be a different voltage, right? Doesn't stay the same.
So bear with me here. If this is water flow. This is we open the first faucet, completely open. And yeah, and the second faucet, are you gonna get the same pressure?
No.
No. Third faucet? No. Yeah, it's gonna have high voltage. I mean, this will get the full-fledged 120. This will get less, like 100 and maybe 100,
The
just
closer to
100.
the source, the higher the
So yeah,
pressure.
so the voltage will drop. And be completely used for the series circuit. Completely. So at the end, if you put your voltmeter here and you measure the voltage here, it's going to be 120. You go in here, leave it in there. See the voltage drop between those two is going to be 100. If you go to here, it's going to be 0. By the end of the last load, it's going to be 0. So that would happen to the voltage, it drops.
What
Make
is the
sense?
current, same,
Huh?
the current, why is it same?
The current is the same. The flow is going to consider the resistances here coming as 1.
Oh, so it just only acts as a one resistance,
Yeah.
not
It will,
three
they will all
resistance.
act as one resistance.
Oh, I see, okay,
Yeah.
I was thinking like. they-
Which actually comes to the next
three
step.
volts.
The next thing, which is the resistance. What happened to it? For these three,
So it's only one resistance.
it's going to be 1.
Oh.
So if this is 3 ohm, and this is 3 ohm, and this is 3 ohm, what is the resistance for all of this? 9. So adds up. So the circuit sees 9 ohms, and it's gonna divide 120 over 9 ohms, and you will get the amperage, which is going to be the same in every circuit. Does it make sense at all? Does the water analogy helps a little bit?
I feel
Drop,
like, you know,
drop,
I don't know,
drop,
it's
huh?
a little confused. If there's a bigger pressure, the current flow should be higher too, isn't it? Why is it
No.
the same current flow when there's a bigger pressure?
I see your point,
Yeah,
but you think if you clip the multimeter here, it should be different, right?
right.
No, but again, this will behave as one resistance. So if you clip it in here, it's going to be the same as clipping it in here, as in there. The flow for the entire current is going to be the same.
Same, yeah, that's
You
what.
clip it here, you clip it here, it's going to be the same. And You can verify that actually when we go in the lab this week and do it. It should clip on, it should be the same, and the flow, because these are going to behave as one resistance.
So when it's pretty much, auto completely, but if I'm trying to figure out what's wrong with the circuit,
Yeah.
I should just go by the voltage, where will the voltage drop, is volume or power? And then I can pinpoint where in the circuit is the problem, so I can fix that area. That's pretty much.
It depends on the situation, but it's good to know that. That's one tool to know. Yeah.
So that's kind of like what I'm trying to see, because if amperage and current remains the same, and the ohms, you just add them up.
Yeah.
So it's not really guiding me
So,
towards what
yeah.
the problem is in the circuit.
For example, if you have this circuit and one of those components went bad,
Yeah.
you're gonna have no current at all. So you can measure the voltage drop, the voltage is gonna be the same, but no current at all, no flow, completely gone. Any question about that? We'll give some examples again. If you can just remember that amperage remain the same in series circuit, voltage will drop, keep dropping until it's completely depleted, and finally resistance will become one. You'll add them together. Good? Yeah. It's tough to visualize because it's electricity, but thinking of the water and water flow should help a little bit.
For the volts, it will always, at the end, go be 0.
Yeah, yeah. That's the cool thing. And hopefully we'll do that in the lab so you can see it. Believe, but I'm not lying to you. I'm not making that up.
How would it still work if there's no volts?
Huh?
How would it still work?
You will see the first light bulb gonna be bright, second one is gonna be dimmer, the last one is not going to light up at all. You will see them drop.
But that's still completing the circuit, that's
Yeah.
what I'm saying. If
It's
still
gonna work,
completing-
it's gonna complete the circuit, but the last light is gonna be dead, nothing. Nothing, you'll see that.
But then there is still a current going through?
Yeah.
But.
No voltage to turn on the light.
you just gotta
Which
know-
also, again, something you have to keep in mind. If something, if one of those components goes bad, and if there's still complete circuit, but it's not running. Yeah,
Does that mean it's overdrawing?
yeah, you don't have enough voltage. So it's really good to know that piece of information. The light bulb is there, it's a complete circuit, but nothing is happening. And you will see the light is very, very, very dim at the end, and there is current going, there is path, but not enough voltage. So we'll do that in the lab so you can see it. How long is the video?
22.
Okay, let's pause here and do that one.